Good morning, class. We are looking at exam 2 review starting with section 2.5, and the session is being recorded. Make sure everything is muted, audio, video, and for privacy issue, please, if you need, you can even change your name to your initials. At the end, when we stop the recording, I answer any questions you may have. So here we go. So we are looking at 2.5 continuity. The synopsis of that is very simple. Continuity takes place when the limit is equal to the functional value. So the idea of limit of f of x as x approaches a from the left, this refers to limit from the left side, this limit from the right side. If the two are identical, the limit exists. Continuity when this limit is equal to the functional value. Okay, now also we have the IVT. We have seen it in previous courses, including college algebra and pre-calculus. If you happen to have a continuous function in a closed interval of a to b, and because it's continuous, it covers everything from a to b, it covers everything from f of a to f of b. That's really the bottom line. So if there is a number in between, f of a and f of b must be covered. It is used to find roots because, for example, if one is positive, one is negative, it indicates that the zero is in between. Now, we want to determine a C such that this piece is continuous. Okay, to do that, let's just see what's happening here. First of all, this is a rational expression. And anytime you have a rational expression, you really have to put it in lowest term. In other words, you can write it in the factored format and factor it. But any rational expression has a domain and it's continuous in its entire domain. Now the domain is all real numbers except 5. So in other words, you set the denominator equal to 0, that is out. Needless to say, this can be simplified, but it remains that x can't be 5 with the original given function. So this is continuous everywhere, from negative to positive infinity, except at 5. And therefore, we have to figure out what happens at 5. In order to make it continuous, the limit and the functional value must be the same. So first and foremost, to take this limit, we do the factoring. We drop the common factor of x minus 5. And you're left with x plus 5. Now the limit of x plus 5 as x approaches 5 when we plug in is 10. And we also know that p, okay, of 5 is equal to c. Okay, if we want continuity, continuity takes place if the limit is equal to the functional value. And remember, this function is continuous everywhere except at x equals 5. To make it so, at x equals 5, the limit is 10, the functional value is c, set them equal, and we are done. Set them equal, and we are done. Here's another one which is fairly similar, okay? So let's look at this example and see what happens in this case. I'm turning off the video to make sure your side doesn't get blurry. Sometimes it does. Show the function is continuous from negative to positive infinity. When that happens, you're dealing with a piecewise defined function. The top one is a trigonometric function, and so is the bottom one. Both of them are sinusoidal functions. And as you know, they both are continuous from negative to positive infinity, sine and cosine functions. So with that being the case, this function is continuous everywhere, but possibly at the endpoint, namely pi over 4. So according to this, it is continuous everywhere. We have to check the pi over 4. So the way it is, without checking, this is true. Why? One more time. Sine is continuous from negative to positive infinity. Therefore, it's continuous from 0 to pi over 4. Cosine, the same thing. Therefore, it's continuous. Therefore, it's the sine from negative infinity to pi over 4 because less than pi over 4. cosine from power 4 to infinity. So that is the case. Let us look at power 4, the endpoint, meaning plug in, come up with the functional value for the bottom one here, okay, because of the equality, the functional value is here. And then you take a limit as x approaches this endpoint, namely power 4. Let's do that. So we take a limit as x approaches power 4 from the left. That means you're dealing with the top branch, and as you know, sine of power 4 is square root of 2 over 2 or 1 over square root of 2 over 2. Let me just write that. You see this one or you see this one, class. That really means the same thing, okay? And you do the same thing from the right, which means you are taking the bottom piece and you look at it. And because they are identical, okay, the limit exists. Also, we have to look at the third piece, which is the functional value. So we looked at this, which really contains two pieces, the limit from the left and right, this part. And the right side, the third piece, f, okay, of pi over 4. Because of the equality, this is your choice. And as you know, that works too. Because the limit and the functional value are identical. And I put square root of 2 over 2 here just to, again, to show you that that means the same thing. Okay. And because this is the case, then it is continuous at pi over 4. Now, we've already discussed that it's continuous everywhere. Perhaps we should check the pi over 4. So from here and here combined, f becomes continuous from negative to positive infinity. By the way, we have a one-sided continuity because of the equality class, okay? So it is continuous from the right side in case it wasn't continuous at pi over 4. In case this wasn't continuous at pi over 4, would be continuous at pi over 4 from the right. Of course, that wasn't the case. The next thing is to look at this case. We are given this function, okay, this equation, I should say, and we want to see if there is any root between 1 and 2, okay? All right, so if we bring everything to one side, and it really doesn't matter to the left or right, okay, so the question part of it is missing. We want to see if this has a root, okay, in a specific interval, okay, of 1 and 2. So let's bring to the left or right, makes no difference, and we give it the name f of x. So so f of x is x squared minus x minus sine x. If you said it's, let's call it g of x, and you said it's sine x minus x squared plus x, that means if you moved it to the other side, it doesn't matter, it still gives you the same thing. This is a continuous function because it's a combination of a polynomial function and a sine function, and therefore it's continuous from negative to positive infinity. Okay. Now, if we plug in, this is by inspection, okay, we can't just solve it like this. This is by inspection. If we plug in 1, the functional value becomes negative, and if we plug in 2, the functional value becomes positive. Why is that? Let me quickly show you. So f of a 1, everybody, is a 1 squared minus 1 minus sine 1 equals minus sine 1, and by 1 we mean radian, okay? What is minus sine 1? Sine 1, remember 1 radian is about 57 degrees. And so it's negative. But if we plug in 2, let me use a different color. f of 2, 2 squared, minus 2 minus sine 2. So this is 2 squared is 4 minus 2, 2 minus, and this is always positive because sine in the worst case becomes, in this case, if it's positive 1, then 2 minus 1 becomes 1. So no matter what this is, positive. And therefore, there is a root between 1 and 2. According to this, if the question was, is this continuous on 2 and 3? If the question is from 2 and 3, okay, we showed that at 1. So between 1 and 2, there is a 0. The reason why, because IVT applies, intermediate value theorem. So what is the IVT? I want to make sure that we understand what happens here. We are dealing with a continuous function from negative to positive infinity, and therefore it's continuous from 2 to 3 or 1 to 2, it doesn't matter. So if the question was, show that there is a root between 2 and 3, we picked up a couple of points. This is by inspection class, 1 and 2 by inspection, and we showed 1 and 2 in between 2 and 3, okay? One of them, doesn't matter which one, gives you a negative value, one of them gives you a positive value, therefore this is the case. Okay. The next one, just remember the definition, okay, for asymptotes, okay? We are looking at the horizontal asymptote in this case, all right? The limit of the function as x approaches either negative or positive infinity gives us a number, then y equals L becomes a horizontal asymptote. As you can see from the graph here, okay, from the graph, an exponential decay, okay, the x-axis becomes the horizontal asymptote. The same thing for the growth, okay, and the reason is very obvious. If you take a limit of f of x, in this case b to the power of x, as x approaches minus infinity goes to infinity, but if you let it go to infinity, it runs along the x-axis. The x-axis has the equation y equals 0. Y, okay, let me write it down. The x-axis, y equals 0. Okay, the same thing happens here. But in this case, as x approaches negative infinity, we have that. Or maybe if we are discussing the infinity, as you can see, this is when x goes to infinity, so does y. When x goes to negative infinity, so does y. This is known as the end. The end behavior. I hope you remember that from, algebra. Okay, so that's that. And then we have over here the definition of a VA, vertical asymptote. We have a vertical asymptote under the following condition, okay? If you take a limit of a function and it blows up to infinity or negative infinity as x approaches either a or a from the left or a from the right, then the VA occurs with the equation of x equals a. As an example, if you look at the function, and everybody remembers the graph, the basic graphs, okay? As you look at this graph, the limit of ln x as x approaches 0 from the right is negative infinity, and therefore, I hope you see that x equals 0. Let me just write it underneath. The VA is the y-axis. Okay. So again, from the graph. We also have a tan inverse, as you can see, where we have two horizontal asymptotes. So those are definitions. All right. Now let's take a look at the limits. By the way, when you do the limits, you stick with what we have covered, meaning some students may have heard of L'Hopital's rule. You cannot use that. We haven't covered that. We will cover it later on. So you have to stick with the methodology that we use. In general, when you want to take a limit class, just plug in and observe. Okay, so plug in. What happens when you plug in? Well, if you get to a number as you plug in, you're done. If you get to a 0 over some number other than 0, that is 0 and you're done. If you get to a number over 0, okay, you have to figure out accordingly if it's going to be negative or positive infinity. It blows up, but is it positive or negative infinity? You want to be able to come up with it. And if you end up with indeterminate forms, such as, let me just write it, indeterminate. Indeterminate forms, we have many of them, such as 0 over 0, infinity over infinity, infinity minus infinity, and more is coming our way. That simply means more work. We have to do our algebraic techniques to figure it out. So, in the case of a rational expression, where t is approach, or t or x, any of them that is the independent variable, is approaching infinity or negative infinity, the technique is to divide by highest degree term in the denominator, which is t squared, everybody, and observe. So here's what happens. Remember, t is approaching infinity, so this goes to 0, this goes to, everything goes to 0 except 1. And because the denominator is a number other than 1, you have 0 over 1, which is 0. We do the same thing here. We divide by highest degree term in the denominator, namely x. And this is what we get. Now let's plug in. This is infinity, this is plus 1, this is 0, this is minus 1. And what's interesting here is that the numerator, by the way, infinity times 1 plus 1, infinity times 10, or infinity divided by 10,000, it is still infinity, okay, or infinity squared, okay. We know the top is infinity, but what about the bottom? The bottom has a sign, and that's important to see. Because it's negative, the result is negative infinity, and you want to be very careful of, okay. In this case, I hope you realize if you plug in, you get infinity minus infinity, class. If you plug in, you get infinity minus infinity. And so the technique is to multiply by the conjugate. So we're going to multiply by the conjugate and divide by it, because this piece in blue is equal to 1. It's justifiable. And then what do? You keep the denominator intact and you multiply these two. I hope you can see that it's a minus b, a plus b. Resulting in a squared minus b squared, right? Which means this piece comes out minus x squared, and you write the denominator. So x squared cancels out negative x squared. And now if you plug in infinity, this is infinity. Remember, square root of infinity is infinity. Infinity plus infinity is still infinity, and the result is 0. Now, it's important for you to know, because it's infinity minus infinity originally, doesn't mean we always get 0. Sometimes we get infinity, sometimes we get negative infinity, sometimes we get a different number. You have to work it out. All right. In this case, we just plug in. Remember, first we plug in. And I hope you realize that this goes to 0. And the reason why, because it's e to the power of negative t. So class, e to the power of negative t is 1 over e to the power of infinity. That's 1 over e to the power of t. And if you replace it with infinity, it's 1 over e to the power of infinity, which is infinity. And 1 over that is 0. That's why. So 12 divided by 4 is 3, and you're done. When we deal with part B, t is approaching infinity, and both of them have e to the power of t. Just we treated this like a rational expression and a methodology. Okay, this is not a rational expression because we have e to the power of t. You divide by the largest piece, which is e to the power of t, the top and the bottom. Let's do that. Let's simplify. Okay, so what happens is this goes to 0, this goes to 0. So you end up with plus 1 over negative 3, or simply negative 1/3. Negative 1/3. Okay. Part C, if you plug in, you get infinity minus infinity, everybody. Plug in, you get infinity minus infinity. So what is the technique? Factoring. Now that we have factored, if I plug in, I get infinity times infinity minus 1. Now, infinity minus 1 is also infinity, and therefore the answer is infinity. If you recall, in the previous page, we ended up with 0, and now infinity minus infinity resulted in infinity. So I hope everybody understands why we have to go through the process. Okay. More limits. We can separate them into two pieces. I hope you realize this goes to 0 because it's e to the power of negative infinity. So this goes to 0. And the other one, it oscillates between negative 1 and 1. This is cosine. Cosine and sine, they oscillate between negative 1 and 1. Therefore, this one doesn't have a limit. The limit, therefore, doesn't exist. Sine and cosine oscillate between negative 1 and 1. That's why. This question, it's similar to what we just did in the previous page. Okay, everybody? We divide by highest degree term in the denominator in the case of a rational. This is not rational, but we treat it as such, and we divide by the largest piece, which is e to the power of 3x. And when we do the math, okay, we simplify. Here's what I want you to notice. When you divide this one by this one, you get 1. When you divide this one by this one, I hope you see what you get. You get minus e to the power of minus 3x, which is minus 6x. Okay? So you're dividing every piece by e to the power of 3x, and this gives you e to the power of minus 6x. Each one goes to 0, you get 1 over 1. Each one goes to 0, and you get 1 over 1. Okay, everybody? All right. Here's the next one. Let's see how we deal with that. Whenever you have a case like this, you should remember that sine and cosine are always between -1 and 1. So ultimately, the squeeze theorem is in order. And so what it means is um, sine is between -1 and 1, and sine squared between 0 and 1. By the way, class, you can, if this was positive, let's say this was 1, this was 2, then you could square them. This becomes 1, this becomes 4 here. But because it's negative, remember, you're squaring it, so that's why you go to 0. I want to make sure we understand what's happening here. If there is a variable between, let's say, 2 and 5, you can square it and it becomes 4 and 25. But it's both sides positive. In this case, negative means then it goes to 0. And so we want to create this expression starting with sine and then sine squared. How do we make up this expression? 1 over x squared plus 1 is missing. Okay, so we are going to multiply both sides by 1 over x squared plus 1. Okay, so let me just write that for you. So we are multiplying by 1 over x squared plus 1, all three sides. Okay, class? And now we can take a limit of each end. Okay, let me use it. So this gives you 0. This gives you 0. Okay, the limit of 0 as x goes to infinity, and you use this one is 0. The limit of the right side obviously is 0. By now you know that. Of course, the proper methodology is to divide by x squared, the top and the bottom. And therefore, by the squeeze theorem, this piece becomes 0. Okay. Limit of tan inverse of ln x. We can ultimately plug in 0 and observe. To do that, you can do it just the way it is, or just interchange the limit and tan. As you know, this is negative infinity, and the reason you know it, I showed you the graph. Again, this has got to do with the graph of ln x, class. I hope you remember that. Remember the graph of ln x. You really need to know the graph of elementary functions, okay? So you know this is negative infinity, okay? And at this point, you can say this is alpha, therefore tan alpha is negative infinity, and the answer is minus pi over 2, okay? This is how we solve the inverse functions in trigonometry. All right. Let's look at this example. We want to find the asymptotes, and remember the vertical asymptotes, they have a definition. Horizontal asymptotes, they have a definition. And for horizontal asymptotes, you have to take a limit and let x go to positive and negative infinity. So when you do that, because we've seen this many times before, I'm not going to go through the process. I hope you realize you have to divide by the highest degree term in the denominator. We also discussed that in pre-calculus in general, if you recall from discussing asymptotes for rational functions. If the degree of the numerator is the same as the degree of the denominator, the leading coefficients take over, so y equals 2/3. This is a fast and easy way to answer that, but the process is to divide by x squared. As far as VA, short for vertical asymptote, set the denominator equal to 0. Now that you do the factoring, set them equal to 0, and you come up with the answer. So again, I hope you remember from algebra, okay, college algebra or pre-calculus, when we were graphing rational functions, we would first and foremost put it in lowest term. That's something which is important, okay? If there's a common factor between the top and the bottom, you must drop, and that generates a hole in the graph, okay? After that, you set the denominator equal to 0 is the vertical asymptote. Then you look at the degree difference, okay? So just to quickly remind you what we did. When you look at the degree difference, if the numerator is, let's say, n of x, and this is d of x, okay? If the degree, so let's actually write it as a sub n x to the power of n all the way to the n, and this is b sub m x to the power of m. If n is less than m, then you have a horizontal asymptote of y equals 0. Do you remember that? If n equals m, then we have a horizontal asymptote of y equals a sub n over b sub m. And if n is precisely equal to m plus 1, we have a slant asymptote or oblique asymptote, and you do long division, or if need be, synthetic division to come up with the answer. Anyways, here's the next one. We want to find a formula for this function based on the given. There are really infinitely many solutions, but to give you an idea, you can say y or f of x equals, so VA x equals 1, so you have a factor of x minus 1 in the denominator. X equals 3, so you must have a factor of x minus 3 in the denominator. Okay, does that make sense, everybody, so far? Now, if you look at the degree for the denominator is 2 and y is 1. Remember, when the degree is identical, it's just that you have the coefficients to take over the leading coefficients. Let me grab a different color class. How about this one? Okay. So now at the top, if you notice, the denominator is x squared, okay, minus 4x plus 3. As long as I have x squared at top, then they have the same, leading coefficient, and the answer is 1. Again, is this the only one? No, there are different ways of writing it. Maybe I can have x squared minus 7. I'm just making it up, okay? Something like that. So this is one way to come up with the answer. Now, a quick reminder as far as the derivative and rates of change. I hope everybody remembers from elementary algebra the concept of rise over run, okay? Slope, the average rate of change of y with respect to x. Means if I have 2 points, I can come up with the slope. Now, as we move q closer and closer to p, gives rise to the slope of a tangent, the tangent line, and therefore the slope of a tangent line, which becomes the limit of m of pq as q approaches p. And here's the definition, okay? And basically, we call it f prime of a. That means differentiation at specific point A, and it gives rise to the equation of a tangent line. Now, what I want to discuss here is the following. You really don't have to memorize that, because I hope everybody remembers the point slope. Y minus y1 equals m times x minus x sub 1. This is it. Sometimes they call this L of x, by the way, linearization, okay? It's coming up. So the moment you hear linearization or a tangent line, just think of a point slope. What do you need? Two things. You need a point and you need a slope. How do you find the slope? Differentiation. So you really don't have to memorize and learn anything new. And if you generalize it, it's the differentiation formula. And for now, by the way, for this exam, we have to use the definition, and there is no other way. And we cannot use the formulas, okay, for certain questions. If a question is asking for definition, you're going to stick with definition. If it doesn't, so be it. I hope everybody understands what I'm saying. So I'm going to repeat. If a question is asking for definition, we want to follow that. All right. I wanted you to, I want to sort of remind you of what's happening as far as the average is concerned. If the distance is given and we want the velocity between 2 points, we are really looking at the average rate of change of, distance with respect to time, which is the average velocity. In other words, if I cover 100 miles over the course of 2 hours, I have the speed of 50 miles per hour on the average. And that's exactly what's going to happen. Elementary algebra plug-in. Okay. So plug in 4 here, plug in 2 here, come up with the answer, and you're done. So this is elementary. This is nothing brand new. What is slightly brand new is this part, which is calculus. And for now, we are going to use the definition, okay, for this question, because it was part of the definition. So according to this formula, we plug in, okay, A equals 4. By the way, if you don't plug in and you keep it as A or even X and finish it, and at the end you plug in, it works for me. But for now, this is it. Now you have to go plug it into this. So this part is this. And I'm hoping nobody has any problem simplifying. I hope you see that this is it. All you have to do is simplify using your algebraic techniques. So there's really not much to it. If your algebraic technique is good, practically you're done. If your algebraic technique is good, you are practically done, class. Okay, so you simplify this. Let me just, okay, so 2 times, so 4 plus h squared, so 2 times. I'm going to write the first step and then you can, 2 times 16 plus 8h plus h squared, and then 5 times 4, and then minus 5h, and then plus 40. So this part simplifies to that. And the numerator, okay, so this is 16, so this is 32, okay. Minus 20 plus 40. So it simplifies to that. You drop the h and you come up with the final answer. And the units, class, it's important to see the units is the units of distance over the units of time, for a simple reason, the definition, which is the limit, and the derivative, which means if I were to write this again, I want to use a different color here. This really means ds dt. So the units of the numerator over the units of the denominator, in this case, the units of a change in distance over the units of change in time. Okay. All right. We want to find the equation of a tangent line. Again, I want to do this with the definition class. With the definition, we are practicing definition, because if there's a question with definition, we want to be able to handle it. And basically, you need 2 things when you're looking for the equation of a tangent line. You need a pair. A pair is not given, only 8 is given, and that's fine. If you plug in, you get 3 times 8, 24 plus 1 is 25. Square root of that is 5, which means the pair is given. So they don't have to give us the pair. If they give us the x, we have the pair. Now we are going to find f prime of x using the definition. Okay, so pay attention to the way you set it up. You replace this x with x plus h. That's all. That's the first one. And as you can see, by the way, if you plug in, you get 0 over 0. As you can see, the technique involved is to multiply by the conjugate. We've done this many times. So you multiply by the conjugate. which means this negative sign, we change it to a positive sign. Now, first I want you to pay attention to the denominator. We really don't do anything, we write it as a product. The reason being, h is approaching 0, and the 0 in the numerator doesn't give us a hard time. It is the denominator that does, and we want to get rid of it, so you write it as a product. The numerator, a minus b, a plus b comes out as a squared minus b squared. And all you have to do, simplify the numerator, everybody. 3x plus 3h plus 1 minus 3x minus 3. Okay. Minus 1, 1 minus 3, minus 1. And so everything cancels out except 3h in the numerator. We are not touching the denominator, notice. And see what happens. We find a way to get rid of the h. That's really that's the process. How do we get rid of the h in the denominator? And this is the process. We did all of this, so this goes away. And it does. Now, if you replace the h with 0, what happens? This becomes square root of 3x plus 1, which is the same as this one. So you get 2 of this. Now, what is the slope? Plug in 8. We already have seen when we plug in 8, this becomes 5. So 3 over 2 times 5, or 3 over 10. Okay. 3 over 10. It's very straightforward, class. And y minus y1, as I mentioned, just write the point slope. So y minus 5 equals m 3 over 10 x minus 8. And I don't think anybody has any problem with fractions, class. Okay, so we can all see what happens next. So all right. Later on, we'll look at formulas and the easy way out. But for now, we wanted to, practice a couple of definition examples. The graph is given, and we want to use it to sketch the graph of the derivative. There are a few things to remember. Okay. Number one, look at these important parts. Those are peaks and valleys, and they correspond to relative extrema, relative max, relative mean, where f prime is 0. Okay. Now, this portion, okay, is decreasing. So f prime is negative, increasing positive, decreasing, and so on. So when f prime is positive, f is increasing. When it's negative, is decreasing. Think of it as a line with a positive slope here and a line with a negative slope here. So if you were to look at this, you start with those easy points. Those are extremely important, class. Okay, so you plot 0 for this one, you plot 0 for this one. Okay, just to give you an idea. So you plot 0 for this one, and for this one. Okay, so this portion is what? Decreasing. So basically, it's below the x-axis. This portion is increasing, but what happens, it goes from A to B. So it goes above, but it has to come back down. Why does it have to come back down? Because it goes from A to B. At A, we have a 0. At B, we have a 0, derivative. And this portion is decreasing, It's below the x-axis, but the reason it has to come back up, again, at some point, has to come back up because, again, goes back to C, where it's 0. This portion also increasing, so goes above. So it looks something like this. Take a look. It looks something like this. Now, this point that was given class, the idea was that if you pick any point and you do your best to do a line segment that represents the tangent line, and if you could do that, and it's not easy, then you calculate the slope by picking up a couple of pairs. So in this case, at 5, use a pointer. At 5, okay, this tangent line has a slope of 3/2, so this corresponds to 5, 3/2. 3/2 or 1.5. That's the idea behind it. Okay. For this graph, okay, I hope you see it's the same thing here. It's 0, okay. Here's it 0. Okay, and increasing, that means f prime is positive. Increasing, that means f prime is positive and therefore above the x-axis. This one is decreasing and f prime is negative, and it looks something like this. Okay, the green one. Okay, so I hope you see y again. So basically this portion corresponds to this portion. Okay, class. And then below, corresponds to this portion. All right, so I guess it's clear. This was done again as in the in the PowerPoints that was done. A function fails to be differentiable at several points, in several cases. One of them is a sharp corner. So first and foremost, we know that. Secondly, if you happen to have a line y equals mx plus b, then y prime is m. And so for any line, with the exception of a vertical line, okay, the derivative function is a horizontal line, y prime equals m, okay? That means then you're going to write y equals 5 or 2 or any number. So all you have to do, calculate this slope. So to calculate this slope, you pick up the pairs and you calculate the slopes. I'm going to assume everybody can do that. Now, what I want you to notice, if you look at this portion, this line segment, okay? If you assume it was just a line, then you would have to draw y equals negative 1/2 as the answer, and you're done. So if this line continued indefinitely on both sides, in both directions, then y equals negative 1/2. But it stops at this point with a hole. The same thing happens. If this was a line, then you would draw y equals 1, so on and so forth. But instead, we get those. And take a look. There's a sharp corner here, sharp corner here, sharp corner here, so on and so forth. So that's how we arrive at the answer. All right. So again, a function fails to be differentiable when we have a sharp corner, discontinuity, vertical tangent line. Now, we want to see what happens in these cases. A function fails to be differentiable here for this one. Here at x equals 0, we clearly have a discontinuity. Over here, it is a vertical tangent line and not a sharp corner. I'll explain it to you after I'm done with the second one. So that's the answer for that one. For this one, again, we have a discontinuity here, which corresponds to this number, which is -1. And we have a sharp corner here, which corresponds to this number 2. Now, if you said this is a discontinuity because you think it's a corner, I have no problem with that. But one of the things that perhaps is helpful is that if you notice, this looks like a V shape, essentially up or down, okay? Even if it's down, V shape. Whereas this one seems that eventually it want to go up like this. So that would be the difference that distinguishes between the two, but it's not that big of a deal. Finally, on this, chapter, we want to find the following limits when x is approaching -infinity. So we want to see what happens. When it's -infinity, things may be a little bit different. You want to be careful. So how do we do that? There are several ways of doing this, okay? Whatever methodology that, of course, has all the details is okay with me. I hope you realize, assuming this was only x to the power of 6, that means it could have come out as x cubed. So in a glance, you notice that the degree of the denominator is 3 and the numerator is really the same thing. So you take out x to the power of 6 in the following manner. This is one way to factor it. Now, if you want to take out x to the power of 6, remember what happens. X is approaching -infinity, okay? So I hope you remember the following, okay? Absolute value of x, okay, square root of x squared is not x. Square root of x squared is absolute value of x. I hope everybody remembers that. And absolute value of x is x if x is positive or 0, minus x if x is negative, because it is defined as what? Distance, okay, from 0. Because x is approaching -infinity, the answer will be -x. Because what this really means, this doesn't mean negative, it means the opposite of x. Do you follow what I'm saying? So it says if x is negative, for example, -5, write the opposite of that, make it +5. That's the concept. So with that being the case, when we want to take it out, we take it out as -x cubed, okay? When x is positive, in other words, if x is approaching infinity, then it comes out as x cubed. But if it's -infinity, it's minus, and therefore you take this out as x cubed, it generates a negative sign. Now, you divide the top and the bottom by x cubed. If you divide the top by x cubed, this goes away. So you get minus the radical. And this one, 2 over x cubed minus 1. Now, if you plug in, I hope you realize this guy goes to 0. So you have only 4 minus square root of 4, which is -2. And this goes to 0 over -1. Negative over negative gives you positive, okay? However, this is the case where x is approaching infinity, okay, class? And so what happens is you can divide by x to the power of 4 if you want inside. See, when you divide the top and the bottom by x squared, out is the same as dividing inside by x to the power of 4. You can take it out and nothing changes sign. because x is approaching infinity. Okay. And so what happens to this one? Okay. So you have 1 plus 0 or simply 1. This, if you want, I can rewrite this inside as 1 plus 1 over x to the power of 4, and this goes to 1 when x approaches infinity. Okay, this goes to 1 as x approaches infinity. All right, so we are looking at chapter 3 review, and we are going to cover the first 5 sections. So the derivatives of polynomials and exponential functions, product and quotient rules, trig functions, the chain rule, implicit differentiation. First and foremost, there are many formulas. Hopefully we are comfortable with those. We have practiced them. Okay. So we are ready to move on. All right. Let's look at a few examples here. Again, remembering all those formulas really are essential. Starting with the first one, I'm going to put a raised dot in between, meaning we are dealing with the product rule here. The product of x squared and sine x. I'm using the shorthand notation, and I'm going to write it, everybody. Fg prime is f prime g times g prime f. That's the shorthand notation. So in this case, the derivative of x squared is 2x times sine, plus the derivative of sine is cosine times x squared. And practically we are done. We are going just to rewrite this. Now, in this case, if you take a common factor of x, doesn't make that much of a difference, but if it does, you must. Okay. For the next one, again, I'm going to use the shorthand notation for the quotient rule. So I'm going to write that the shorthand notation f over g prime, we are going to use f prime g minus g prime f over g squared. Now, one thing I want to mention to everybody, and let me just write, this is f and this is g. There are, if you look at my PowerPoints, these are the two that I have there, or even if you go to the previous page. The reason I have them like this is a plus sign. Believe it or not, this is a plus sign class. F prime G, it does plus, okay. The reason I use that, it is helpful memorizing this one. Take a look. If you use f prime g plus g prime f, the numerator, all you have to do, change the plus to a negative sign for the quotient rule, and then over the denominator square. That really makes it easy, I think, to memorize. Okay, so in this case, the top is the f function, the bottom is the g function. So you take the derivative of the top, 1 gives you 0, sine gives you cosine times the bottom. So this is f prime cosine times, so f prime g, minus g prime, the derivative of the bottom is 1, plus the derivative of cosine is negative sine, okay, times the top, 1 plus sine, over, just write the bottom in a parenthesis and square it. And this is the end of calculus class, believe it or not. So all you have to do is to rewrite this and simplify the numerator. So we have cosine x times x. So we have x cosine x. We have plus cosine squared. Okay. Now this product is what? I'm going to write it here. 1 minus sine squared. Okay, class? And 1 minus sine squared is the same as cosine squared. Because I hope everybody remembers the Pythagorean identity, one of them sine squared plus cosine squared equals 1. And so with that being the case, now what do we have? Take a look. We have cosine squared x, and then this is a negative sine and cosine squared x. They cancel each other, so the numerator has nothing but x cosine x. And you don't have to square the bottom, you're done. Okay, so that's simple. Here's the next one. Again, we are going to use this shorthand notation, f prime g minus g prime f, where f is the numerator, g is the denominator. So let's write it. So this is the f function, this is the g function, okay? If you write it this way, it's really helpful, class. So according to this formula, first we need f prime, then times g. So f prime, 1 minus secant squared. 1 gives you 0 minus, okay. Secant gives you secant x tan x. You write that. Times the denominator, which is tan x. G. Minus g prime. So you're going to differentiate the tan, which gives you secant squared. So minus sign. The derivative of that is secant squared times the top. And the bottom, just write it, square it. Okay. And now you can factor things out and simplify. Okay. This is negative secant x tan squared. Okay. This is minus secant squared. Okay. And this is plus secant cube. Okay. So you can factor them in any order you want. You can take out the secant in general. So secant is in common. Secant x is in common. So you take out the secant x. The first one gives you minus tan x and tan x. Let me just put them together. So these two class tan squared x, okay. This, let me just write this. Okay, minus secant squared x plus secant cubed x. So take a common factor of secant x. Okay, so the first one gives you negative tan squared. The last one gives you positive secant. So I did a different order. You see why in a moment. So I did this one and it gives you positive secant squared. And minus secant squared, if you take one of them out, you have only one of them with a negative left. Why did I do that? Because this was a Pythagorean identity. Another Pythagorean identity is tan squared plus 1 is secant squared. Okay. In fact, let me write one more. We're not going to use it here, but you know, the other one is 1 plus cotangent squared is cosecant squared x. Okay, so there are 3 Pythagorean identities, and as long as you have this one, you can prove the other 2. And so with this being the case, class, okay, if I take the tan squared to the right, it becomes minus tan squared plus secant squared. These two add up to positive 1. That's why I put this next to that. And so it simplifies as follows. Secant x is a common factor. We have it out there, and then 1 minus secant x, and it can't be simplified. By the way, some people write this stuff in terms of sine and cosine. If you remember, when we wanted to prove things in the beginning of trigonometry, we did that. That's not what we are doing here. So, a quick recap. We have used the product rule here. Fg prime is f prime g plus g prime f. This will help us memorize the quotient rule. We use the same thing in the numerator. We change it to minus in between over g squared. So it makes it very easy to remember this. Anytime you are differentiating an expression where the numerator, when you have a fraction and the numerator is a number, can you use the quotient rule? Yes. Should you? No. I would just not use that. I would rewrite this algebraically by putting it to the power of 1/2, bringing it up and make it negative 1/2. And therefore, I can use the extended power rule now. Okay, class, I can't emphasize this enough. So, use the quotient rule when you must and avoid it when you don't have to. Okay, and if you don't realize those, it makes it more difficult. All right, so we are going to discuss the extended power rule. The extended power rule, remember x to the power of n, everybody. When you differentiate, n becomes the coefficient, x n to the power of n minus 1. So the same thing happens. N becomes the coefficient, x to the power of n minus 1. Now we're going to use g of x to the power of n minus 1. Now the derivative of x, everybody, is 1, and we don't have to write times 1. But the derivative of g of x is not 1, it's g prime of x. That's why we must. This is by the chain rule. Okay. So again, the derivative of x is 1, so we never say times 1. But for g of x is g prime, that's the concept of a chain rule. So with that being the case, 4 is a multiplier, it remains 4 times negative 1/2. So negative 1/2 sits in front, 4 times negative 1/2. Now you take away 1 from the exponent. So negative 1/2 minus 1 becomes negative 3/2 times, by the chain rule, we need g prime, the derivative of the inside, which is 2x. And this is it. This is the end of calculus, everybody. So what do you do next? Algebra. Okay. So obviously 4 and negative 1/2, that gives us negative 2. And 2x, that gives us negative 4x, negative 4x. This one times this one times this one. Now this goes down and makes it positive 3/2. And positive 3/2 means the cube, the square root of cube. There are, maybe I write a couple more things here. This is minus 4x over x squared plus 3 to the power of 3/2. And that's what you get. And by the way, you don't have to, as far as I'm concerned, okay? You don't have to, as far as I'm concerned. But if you did, do the following. And you rewrite it in the following manner, because the exponent 3 inside is larger, that's fine, okay? Again, by no means you have to do that, but in case, if you did that, because sometimes in algebra, we did that, and I hope everybody remembers that. So with that being the case, let's go to the next one. All right, so we are looking at, again, the extended power rule, if you will. Okay, and to do that, we bring the 5, we bring the 5 in front, the same thing to the power of 4. And then we differentiate this using what? The quotient rule. F prime g minus g prime f over g squared. So 5 sits in front, the same thing to the power of 4. Now the derivative of this piece, the top is 2 times the bottom minus the bottom is 1 times the top over bottom squared. So let's quickly recap. 5 becomes a coefficient. Same thing to the power of 5 minus 1. Differentiate this piece by the quotient rule. The top gives you 2 times the bottom minus the bottom gives you 1 times the top over the bottom squared, and you are done with calculus. Now we are going to simplify, okay, class, by simplifying this piece first, and we have, just write it here, 2x minus 16 minus 2x minus 3, and the whole thing changes to negative 19. So the numerator of the last fraction is negative 19. To make sure everybody understands what's going on, you can go to the last step from here, but in case, let's rewrite this so there's no ifs and buts about it. So we're going to write this as 5. We're going to write this as 2x plus 3 to the power of 4 over x minus 8 to the power of 4. And then this is negative 19, this is x minus 8 squared. The only reason I'm writing this, because from here to the last step, I don't want anybody to get confused. And so what's in the numerator is 5, 2x plus 3 to the power of 4, and negative 19. So you multiply these two, you get negative 95. This is 2x plus 3 to the power of 4. This one is x minus 8 to the power of 4 plus 2. If you saw it from here and you did that in one shot, more power to you. I just don't want anybody to get confused. So that's using, again, the extended power rule, the chain rule, you know, whatever you want to call that. The general power rule. All right. In order to do this without any confusion, it's important to see what is you're looking at FOG, the composite function, right? It's important to see what is the shell function, the outer function. So the way I do this is, first I read it according to the formula. I'm going to read it as cosine, and I'm going to stop, and I'm going to pause. Cosine. When I read it this way, it tells me my main function, the shell function, is cosine. So I'm differentiating cosine. What is the derivative of cosine? Negative sine. So again, ignore this one for now. And so you're going to write, okay, cosine, and you're going to read cosine and pause. Cosine, the derivative is negative sine. Okay, let's pause. Now, of course, sine and cosine, they need an argument. So you must write the argument. So cosine gives you negative sine. But cosine of what? If it's x, if it's t, if it's theta, you're done. But if it's a function of that, you're not. And now it's a function of t, so you need the derivative of 3t to the power of 4, 12t cubed, and you rewrite it. So if you want to get this right without any problem, the way you read it, it will help you. Just read it as cosine and stop. Cosine, you need negative sine. Okay. All right. Let's look at more examples. First and foremost, when it comes to exponentials, always the derivative is itself. But there may be other things involved. So remember, e to the power of x, the derivative is e to the power of x, okay, class, if you differentiate. So if I'm differentiating this one, the answer is e to the power of 10x. Okay, now, Because the exponent is not x, is a function of x, then I need the derivative of that, which is 10, and I put it in front. This is using the chain rule. Same thing happens here. For part B, it's exponential. So first and foremost, what's the answer? E to the power of 10x. Because the exponent is not x, is a function of x by the chain rule, I need the derivative of 10x, which is secant squared, and I'm done. So again, exponential, the answer is itself. The derivative of 10x is secant squared. You don't have to change the places. This is done, and that's the end of the story. What happens when the base is no longer e? I've gone over the proof. I've shown you that what happens is, even though the base is not e, you still get the same thing. However, you have to multiply by natural log of the base. And I'm explaining it to you here because of the logarithmic properties. Hopefully everybody remembers, okay? E to the power of ln x is x, okay? Ln e to the power of x is x. These two refer to the fact that natural logs and e to the power of x are inverse functions. And because of that, what happens for this one, the answer is itself, and then times natural log of 3 because the base is not e. And as you look at this case, okay, what happens if the exponent is a function of x? Well, you repeat the same thing. See, this one you need, this one you need, and then because this is f of x, you tag along f prime. So what happens in this one, in this case, let's just quickly write it together. So in this case, we are going to write, because it's an exponential function, the answer is itself. Because the base is not e, we need natural log of the base. Because the exponent is not x, we need the derivative of 7x. That's it, okay? And you just rewrite it. The way you rewrite it is important, class, because it's awkward if you put that without the parentheses. One might think it's 7 ln 22 to the power of 7x. So this is the way we write it. All right. We want to take a limit. And to do that, we are going to use what we have discussed in this course so far. The limit of sine over theta is 1 when theta is approaching 0. So the limit of sine theta over theta when theta is approaching 0 is 1. The limit of cosine theta minus 1 over theta as theta approaches 0 is 0. These are the ones that we can use so far, okay? So, as long as, okay, we understand the concept in this case. If it involves sine and the following is true, the argument of sine with the denominator, with this one, the limit, theta approaching, those three must be identical, class, for this to be 1. For example, they can be x, or they all can be 5x, or they all can be, I don't know, m. This is m, this is m, this is m. And that's important to understand. Now, this is 3x, this is 5x, this is x squared, nothing is like that. We have to make all of them look the same, okay, if we can. What matters is that the denominator has x squared, so that makes it possible. So for 3x, class, we want to remember this one, and this one. For 3x, I need a 3x. For 5x, I need a 5x. And if x is approaching 0, so is 3x, and so is 5x. So that will be taken care of. That is not a problem. So x squared is the same as x times x. So that's good. So if I need a 3 here, then I have to put a 3 to undo it up here. If I need a 5 for this one, then I need a 5 here to undo it. In other words, first class, you can, I hope you can see that I can say, okay, in essence, if I put the x here and think of this as 1, and x here and think of this as another one, I hope you see that works, right, so far. Now, the next thing is that, as I mentioned, remember, the argument of sign is 3. You can't change that. Okay, if you did, that means you're uncomfortable with the concept of a sign. Don't do that. So you need number 3. So I can put number 3. That means, how do I undo that? Then I put a 3 in the numerator. In the denominator, I can put 5. Then in the numerator, I got to put 5. So I cut this into 2 fractions. And I put x and x. Then I put 3. If I put 3 down here, I put 3 up here. If I put 5 down here, I put 5 up there. So take a look. So again, I've separated the x squared into x and x. Then this is number 3, so I need number 3, and these two cancel each other. And the same thing here. Now, I separate this from this one. And again, x is approaching 0. I need 3x for this one. X is approaching 0. I need 5x for this one. Not a problem. So take a look at what happens. For this part, I can take the 3 out. And the reason I can say 3x approaching 0, because if x approaches 0, everybody, that means 3x is approaching 0. That means 5x is approaching 0. And that's what happens. So each one, so take a look, this one is identical to this one, is identical to this one. You can think of it as theta. So this whole thing becomes 1. Same thing for the second one. 3 times 5 is 50. Okay, that's the way you approach that. I hope everybody's okay with that. Okay. If you follow this one, you're in good shape. You can handle just about anything you come across. All right. Again, remember what we want. We want this one, and this one to be identical. So I hope you see that in this case, sine of sine x, that means the argument of sine itself is a sine x. So let's take this one down. You know, cosecant is 1 over sine, right? And so I hope you see now what happens. I hope you see that if you think of this as theta, you think of this as theta. Well, we don't have theta here, but you know that if x goes to 0, sine x goes to 0, so I can change that to sine x. So I let all of them be theta. So let sine x be theta. Okay, and so now that results in 1. All right, now notice what happens. The argument of sine is x squared. You cannot change that, class. The argument of sine and cosine remain unchanged. So what can you do? Well, again, go back to this one. You want this one and this one and this one to be identical. So can I make this look like that? Yeah, if I multiply it by x. But if I multiply this one by x, then I'm going to multiply the numerator by x. It's fine. If x approaches 0, then so does x squared. So that's not a problem. So let's multiply and divide by x. Take a look. If I multiply by x and divide by x, this is what I get. Now this is x squared. So I'm going to separate this one from this one into the following manner. Okay. Now this one, x is approaching 0. This one, Since x approaches 0, it's the also x squared approaches 0. That's why I'm changing it to x squared. And now this is identical to this, identical to this. You can imagine it's theta. The first one gives you 0, the second one gives you 1, and the answer is 0. Okay, the limit of x as x approaches 0 is 0, everybody. All right. We want to find the points for which the tangent lines are horizontal. I hope you remember horizontal lines have slope equal to 0. So all you have to do, find the derivative which represents infinitely many slopes and set it equal to 0. This is a simple task. Take the derivative, 3x squared minus 6x. And if you set this equal to 0 and solve, set it equal to 0. Factor, it gives you x equals 0, x equals 2. So at x equals 0 and at x equals 2, we have that. Now, the reason I put this in a pair, I want to make sure everybody understands. When we say x is 0, x is 2, it doesn't mean the pair 0, 2. So 0 means plug in here, the pair 0, 5. 2 means plug in here 2 cubed minus 3 times 2 squared plus 5, which is 1. And that's the reason. Most of the time, if you just said x is 0 and x is 2 is good enough, I don't want anybody to be confused what it means, okay? Now we want to find an equation of a tangent line, and as always, we need two things. We need a pair, we have it. We need the slope, and I'm going to put a raised dot in between and differentiate this using the product rule, f prime of x, and then when I plug in 0 becomes the slope. So let's do that. F prime of x equals e to the power of x gives you itself times cosine x, and plus cosine gives you negative sine x times e to the power of x. It is a good practice to factor out e to the power of x. If you didn't, it's not a big deal for a question like this because you are interested in finding the slope. So let's plug in 0. How do we get 1? I want to make sure that everybody can see that. If you plug in 0, you get e to the power of 0 times cosine 0 minus sine 0. Now e to the power of 0 is 1, cosine 0 is 1, sine 0 is 0, and so we get 1 times 1 over 1. Now, because this is the y-intercept, you can use y equals mx plus b. M happened to be 1, and so is b. Okay, it's not the case always. It happens to be the case here. Okay. So, to recap this page, we want to find points where the tangent is horizontal, find f prime set equal to 0. We want to find the equation of a tangent line. We need a pair is given, and use the x, find f prime, set up x equals 0 in there, replace the x with 0, find the slope. Okay. Implicit differentiation. We want to use implicit differentiation to find y prime or dy dx. In short, implicit differentiation is used when x and y are on the same side and we don't want to solve for y, or we cannot solve for y. That's the idea. And so it is important to know when you do the differentiation class, when x is the independent variable, if x is the independent variable, the derivative of x is 1, and the derivative of the 1 y is y prime or dy dx. That's the meaning of it. So let's do that. Extended power rule, 4 sits in front, the same thing to the power of cube. Now the derivative of the inside, 2x gives you 2, y gives you y prime. X gives you 1 minus 2y prime. And you are done with calculus. Now, I'm done with this as far as calculus is concerned. So in order to get to y prime, there are several ways. And I'm taking a different approach on that. I want to discuss that. You can completely ignore it and do it on your own. You can distribute everything and then bring all the y primes together and solve. I figured because this is a parenthesis, it's easier if we use it slightly different. Understand 2 times this and then y, in other words, distribute it this way. 2 times this makes this one 8 and y prime times this. Okay, so 2 times this makes this 8 and y prime that times this mess. Why am I doing it this way? Because now I have kept the y prime completely separated from this. Okay, now I'm going to bring negative 2y prime this way, and I take the red one to the other side. In other words, okay, this one becomes positive on this side, and this one is negative. Now, I hope you see on the left side, I can factor out the y prime easily because this is completely isolated from this. So this plus 2, right? Y prime is, let me write this intermediate step, everybody. So on the left side, y prime times, and here's the right-hand side. And I'm going to use a blue one. See, this one is 4 times 2x plus y cubed plus 2. So now divide the right side by the brackets and you're done. Okay, everybody? I hope you're comfortable with that. Here's another example we want to look at. Okay. All right, so we want to differentiate this, and we use implicit differentiation. Okay, so sine y, this is question number 2. Okay, sine y. So the derivative of sine is cosine. So cosine y, and because it's y, dy dx of y prime. Okay. Plus 2x cubed times y squared. We put a raised dot in between, so we use a product rule. Let me use a raised dot in between. And so 2x cubed gives you 6x squared times y squared, and y squared gives you 2 y prime times 2x cubed, and the right side is a number, gives you 0. So this one class, okay, so 2x cubed, let me just write this. This gives you 2x 2x cubed gives you 6x squared. We have that 6x squared y squared. Okay. Plus, now the next one, I want to just write it as first y squared is 2y dy dx times 2x cubed, resulting in this. And you're done with calculus. All you have to do just rewrite the whole thing such that you solve for dy dx. The way you do that, you are going to move this and you are going to factor the dy dx from these two pieces. When we do that, this gives you a cosine, this gives you 4x cubed y, and the middle piece moves to the right, makes it negative 6x squared y squared. Now the right side divided by the parentheses gives you the final answer. Okay, everybody? The right side divided by the parentheses gives you the final answer. Okay, and if you look at this question, first of all, we looked at inverse trigonometric functions and their derivative, and we proved that using implicit differentiation. Now we are going to differentiate this and use the fact that these are, the derivatives d dx of sine inverse is 1 over square root of 1 minus x squared, and cosine is the same thing with the negative at top. So basically, it's the negation of that. To do that, number one, we're going to change this to 1 minus x squared to the power of 1/2, so it can be done using the extended power rule. Now, put a raised dot in between. Let me do that. So it's x times the cosine inverse. X gives you 1 times cosine inverse. Plus cosine inverse gives you negative 1 over the square root of 1 minus x squared times x. So that's that. Minus, now this one, 1/2 sits in front, the same thing to the power of 1/2 minus 1, which is negative 1/2, and then the derivative of the inside is negative 2x. So let's quickly recap. X gives you 1 times the second piece. Second piece is a cosine inverse. Gives you negative 1 over square root of 1 minus x squared times the first piece, which is x. So that's that one. Now this piece minus, okay, 1/2 sits in front, the same thing to the power of 1/2 minus 1 or negative 1/2. So the derivative of the inside is negative 2x. Okay. Let's see how we rewrite this. This is cosine inverse, just right. This one is minus x over square root of 1 minus x squared. How about this one? Negative two with this 2, and this negative makes it positive, and they cancel. I hope you see what we have here. This is a negative. Think of it as negative 1/2. This negative 1/2 and this negative 2 cancel each other. They give us plus 1. This one, so in the numerator you have x. In the denominator you have 1 minus x squared to the power of positive 1/2. So right here, you have plus x to the power of 1 minus x squared to the power of positive 1/2. Which is the same as square root. They cancel each other. And we get cosine inverse x as the only and final answer. Okay, class? So the answer becomes cosine inverse x.